Yes, great, great. So, droid autopsy. Well, I'm a forensic investigator, so I guess I have a little bit different talk than most talks today and tomorrow. This is not really about hacking. This is more about the investigation on a device, in this case, Android devices. Me and my team, we worked on the Digital Forensics Research Workshop Challenge last year. It's a really cool challenge. If anyone is interested in this area, I can really advise to join this year or next year. It was about an investigation on 2 Android devices, and today I want to take you through the challenge, how we solved it. It's partly about the challenge itself, but also about the interesting aspects of investigations on Android devices that it touches. So I have probably way too many slides today. I'll try to make pace to get it all put into an hour. So I hope that's going to work. Well, anyway, if you have any questions, don't hesitate to raise your hand, or at the end there's maybe room for questions, I hope. So let's get started. So the challenge starts like this. There is a suspicious death. The guy named Don Norby, I'll refer to him as that guy because that's easier for the rest of the talk, and my experience is that referring to it as that guy is better for the association in the story. So, well, he's found dead with a bullet in the head, and beside him lays an Android 2.1 phone. And the question is, what happened here? Is this a suicide or did something else happen? And there's another case at the same time at a company called SwiftLogic, where the people, they experienced a data breach. And one of the employees, Job Taal, I call it the SwiftLogic dude, he is, well, they have reasons to believe that he is involved, and he would maybe have leaked the data through his Android phone, so he willingly gives his phone for investigations. Now, that's the start of the case, and now the question is this guy guilty of data leakage, or did something else happen? Well, the first thing you do when you get an Android phone as an investigator is you want to perform the data acquisition, so you want to get the data out in a forensically sound manner. Well, what are the interesting storage areas in a smartphone, in an Android phone? The memory card is one thing, of course. The other main thing is the internal storage. And, well, in most smartphones today, that's NAND flash storage. And it has multiple partitions. Well, Android phones, the most interesting partitions are, in this case, the cache partition and the user data partition, where the user data is stored. So this was actually already done at the start of the challenge. So they delivered us the images which they would have acquired in a forensically sound manner. They did describe how they acquired it. Well, for the first case, for that guy's phone, they rooted the device and they used the well-known method, DD, to just make a data dump of the MTD block device. Because as most of you probably know, the Android is just based on Linux, and the NAND flash is represented as an MTD block device in the Linux subsystem. So they dumped the data of the block device using DD to an image file on the memory card. Later they pulled the memory card out and they just copied the image to an analysis system. This is not a really good thing because if you use DD on MTD devices and you use it on the block layer, you forget to take with you the out-of-band bytes of a flash memory. I'll get to that a little further in the presentation, what the out-of-band bytes exactly, why you need them. But this is one important failure in the acquisition phase. Now for the second, the SwiftLogic dude, they rooted the device and they used the correct method, and that is NAND dump. NAND dump, actually you dump all the bytes from an MTD device, and you do it from the MTD device directly, so not from the MTD block, which causes you to take with you the out-of-band bytes also. And they, in this case, they actually transferred it over the debugging port to the system, and they wrote it there to an image file. So the result is we got delivered a lot of images for each partition. On the phone, we get an image. We focused our investigations on the memory card, on the user data partition, because that is the partition where the user data is stored. The cache partition is a partition that is used to temporarily store stuff, like, for example, if you visit web pages, caching is stored there. There's also a system partition. We didn't really investigate the system partition, but it can be interesting in other investigations. For example, if you want to investigate more advanced forms of malware which may alter stuff on the system partition, which was not the case in this challenge. So we skipped that. We focused on the user data partition and the memory card. So where do you start? Well, we have a lot of tools in the forensic investigation area. They're maybe not so known to you, but NCase and Forensic Toolkit are the most known tools, which are actually just really big software packages that you can put in an image and it will decode it for you and index it for you, and you have all kind of cool features which you can directly use. These work on images with known file systems. The SD card, the memory card, is formatted as FAT32, so that's a known file system. We did analyze the SD card with the known toolkits. We got a lot of information from there in this phase. We used carving methods to carve out information from the internal partitions which were not formatted with a known file system. They were formatted YOFS2. I'll come to that later. But if you don't know the format of the file system, you can still use carving techniques to try to carve out known files based on the file signatures. So we use the traditional file carving tools like Scalpel and Photorec to try to get the most out of the raw images, see if we can get any useful data out of that. That didn't go so well, and I'll get to that later too. What we did find on the dead guy's device, on the SD card, you see that there are PDF files stored in the download folder. Well, the download folder is, as you would have guessed, the folder where files get stored when you download them from a web page. But they contain schematics of Swift logic. That's interesting because what has the dead guy got to do with Swift logic? So this was the first hint that these cases are connected. So there's Swift logic schematic files on the phone of the dead guy. We also carved for HTML files. HTML files are nice files to carve to because you can pretty much, based on the markers in HTML files, carve out really nice complete files. And we found this particularly interesting page. This was found in the cache partition. This appears to be a directory listing from an Apache web server. The nice thing is we can see the IP address. So apparently the dead guy visited an Apache dir listing at the specified IP address in the directory SS and saw there 9 PDF files. And this, of course, matches with the PDF files we found in the download folder. So that would make sense. He visits this page, downloads each of these PDF files. They get stored in the download folder. Unfortunately, we couldn't reach the HTML page live. It was protected by an HT access mechanism, and we had to keep it real, so hacking the page was not allowed. So that's an interesting finding. So somehow PDF files from Swift Logic got sent to this web server page and were downloaded by the dead guy. So those were the first findings we actually got without going to more advanced techniques. So we used the traditional carving tools and the traditional forensic toolkit to get these findings. So we got a long way, but then there is still the internal memory formatted in JOVs, which keeps a lot of data to itself because we couldn't get to that data because the traditional carving tools don't really perform well, and our toolkits don't understand the JOVs file system. So if you load it into the toolkit, you just see this big blob of data, and it doesn't really reconstruct the file system, so you can go through the directory and look at the files themselves. So even though our toolkits don't understand the JOVs file system, there are, of course, methods to reconstruct the JOVs file system. You just need to put a little bit of work in that. So there are more ways to roam. One is you can use mobile forensic toolkits, which are expensive. So we wanted to keep it with methods which are free or either not too expensive, so this was not an option. You could use the Android emulator, which actually also works with data images. However, the Android emulator doesn't really like foreign images. You can just tell the emulator, okay, create an Android 2.1 device, and here are the user data image and the system image, because it will start complaining that it doesn't match with what it actually has in its boot image, for example. So that needs some tweaking before you got it to work. The easiest method was to just load the JOVs2 support into our Linux kernel, because, like I said, the Android systems are just based on Linux, and they have JOVs support, so it should be possible to just load it in, and it is, and it's not too hard. Well, the first thing you need to do is load some necessary kernel modules, the MTD, the MTD block, and you need NANSIM to simulate a NAND device in your Linux subsystem. Well, when you include the NANSIM module, you need to make sure you have the right parameters to simulate a NAND device with the correct size and page size and array size. So this is one example we used. You can tweak it to create a NAND device of the right size. Well, then we wrote the bytes from our image to the simulated NAND device. And here you have to mind that with the image of the Swift logic guy, we did have the out-of-band bytes. And if you write it to a simulated NAND device, you should make sure that you write the out-of-band bytes, or else you still cannot reconstruct the JOVs file system. So use the right switches there. Well, the last thing is to download the JOVs2 package. It's out there. And you can just compile it and insert it into the kernel. And voila, there you go. So you mount it with JOVs2, and here you see the example of a user data partition mounted. Now that we have a mounted device, so we actually reconstructed the file system, it's useful to start searching through the files. We could have searched through the image, of course, but if you found some interesting strings in there, you still have to find the origin of the string. So what is that blob of data where I found that string actually representing? So now that we have reconstructed the file system, it's easy to search through it and see in which file a certain string belongs. So in this case, we found the IP address, which is interesting because that's the IP address of the web page we saw in the dead guy's phone. And we found that IP address on the SwiftLogic dude's phone. So that's interesting. What is that IP address doing there? We found it in a Dalvik cache file. Android's packages, programs, applications run on a Dalvik virtual machine. And for each application, a cache file is created, which caches, for example, used strings. And we found it in a cache file of this application, com.android Android.mm. Right, well, that's interesting. First, why is the IP address in there, and why is there a package named Android instead of Android? I don't know if that was actually a mistake of the guys who created the challenge, or that it was somebody who just thought, well, let's make it easier for them and make them recognize a file that's not supposed to be there. Okay, so we have a new lead. Let's find out what this application, this com.android.mn actually is. Android keeps a listing of all installed applications. Whenever you install a package, it's registered in an XML file, and it registers certain information about it, like, for example, under which user ID it runs, when it is installed. Now that's interesting because we can see that's installed on the 5th of May 2011, and I didn't include the whole timeline, but 5th of May was the date when the Swift Logic dude actually bought his phone at the phone store, and this package was installed just before he picked up the phone at the phone store. So that's an interesting find. What's more, what you see here is the permissions. All Android applications can only do what they are permitted to do by what they define to be needed on permissions. So whenever you create an application, you would include a manifest file. We'll get to that later. And it lists the permissions, the things the application would like to do. So that's when you install an application, you see the listing of, hey, you want to install this application, it needs services that cost you money, or it needs an internet connection, and then when you click accept, it gets installed, and the permissions are listed in this packages.xml file. What we also see around the same time, just a minute before, there's an application called com.vzw.SMSProvider, which is also installed. Okay, that's interesting, especially when you look at the permissions. Apparently, this is an application that wants permission to send and receive text files, text messages, sorry. Okay, so now we want to start analyzing the package, the application itself. Well, you can do a live analysis, so just get out the emulator, get the package file, the application file from your images and load it into the emulator and run it. Now the emulator allows you to monitor certain activity in the emulator by, for example, watching log files for debug messages. You can use Wireshark to intercept all internet communication that it uses and analyze it. There's also a Dalvik debug monitor, which you can use to monitor the activity of your application. So, for example, it's heap activity or other things. Well, we mostly relied on the static analysis. So that's the nice thing about Android applications. It's that it's just well, a certain form of Java bytecode, which is pretty well decompilable. In this case, especially because it was not obfuscated. So that's very nice. If you decompile it, you can pretty much look through the source code as if it was the original source code. So you retrieve the APKs, and the APK is the package file which is used by Android for the application. So a package file actually contains the classes of the application, the actual bytecode. It also has a manifest file, which actually tells the system, okay, this is the application, this is the permission it uses, it triggers on these events, that sort of stuff. You can get that Android manifest file out, but it's in binary XML, so you need to convert it first, and there are tools for that, for example, the APK tool, which you can use to convert it to a readable XML. So now we can read the Android manifest file and see, okay, what's the intention of this application. I will show you that in a minute. And there is the Dalvik VM text file, which is actually a set of class files. The Dalvik VM operates a little bit differently than the regular Java virtual machine. So you need, if you want to analyze it, convert it to a regular jar file first. I use dex to jar for that. And the jar file can be decompiled pretty well using, for example, JDGUI or any other Java decompiler. Okay, so this is the Android manifest file of the Unreal.mm. So what you see here in green is it states its permissions. So what does the application want to be able to do on the phone? It wants to be able to transfer and receive stuff over the internet. It wants to be able to read the phone state. The phone state, for example, is changed when an incoming call is received or an incoming text message. When that happens, an event is fired and it's able, now the application is able to actually read the phone state and say, hey, what happened to the phone? Oh, there's an incoming call. So it can react to that. A boot completed event is received. So whenever somebody boots the phone, this application responds to it. It receives a trigger and can start doing things. And whenever an outgoing call is made, this application will actually intercept the outgoing call and do whatever it wants with the event. Then there's the receivers, and those are actually the triggers. So when you develop an Android application, you have an application actually trigger on certain events, and this application triggers on the event when the airplane mode is changed, when the boot sequence is completed, and when the screen turns off. So then it activates and starts doing stuff. And the interesting thing is in the bottom you see in red that it defines a service. Normally when you create an application, usually use activities, which is just a screen that gets represented to the user. When you see a service in a Android manifest file, it's more like a background service that is run. So this application is actually never presented to the user, it just silently boots up on one of the events and starts running in the background. Oops, sorry about that. This is the Android manifest file of the com.v provider, SMS provider. Here you also see the receivers. There's also no activity, there's only a service, so also this application just runs in the background. And you see that the receiver, it receives intents on action send and SMS received. So whenever somebody fires an event especially meant for this, the event is named action send, this application wakes up and starts doing stuff. Whenever an SMS is received on the phone, so the event is just broadcast through the phone, this application picks up the event and says, hey, there is an SMS received, I need to do something. So now when we look at the com.nreal file, we saw that it triggers on certain events, and you want to know, okay, what does it do when it triggers? What is it actually doing? And well, there's a lot of code that just took out the relevant snippet from the code. And what you see here is that it actually it gets the files from the external memory card. It creates its own zipper class, which is actually, when you look at the implementation of the class, it actually just sort of zips the files. And it stores the zip in a file called temp. And then it sends the file out, and you see the function send file, which actually just sends it to the internet. And the interesting thing here is that we have an IP address, and that's the IP address we saw earlier. So apparently the files are zipped and sent to the web server we saw. And you see also that when it has sent the file, that it sends a text message. And that function is actually implemented in the other package, the SMS Provider package we saw. Here you can see that there's also a class in the SMS Provider which triggers on a certain intent. For example, the extra state ringing. That means, okay, whenever an incoming phone call is received, so the phone rings, this application wakes up, And what it does, it creates a string with call in, and it puts in the number and the date and time that the call is received, and sends a message. And when you look at the send message, you can see that it actually just sends a text message. Well, it's maybe not clear, but it sends a text message to, here it is, to this phone number. And this is the phone number belonging to the phone of the dead guy. So this is an interesting application, because this is actually how Android malware, how easy it can be created. Now, this application was not available in the Android market. It was probably installed by somebody in the phone shop. But you see that all these functions are just regular system functions. The only thing that normally needs to happen is when a user installs it on his own phone, he just reads the permissions, and yeah, well, maybe you guys read the permission, but I bet 80% of the people don't even look at the permissions and just say, okay, click through. Or you say, hey, this application needs permission to go on the internet, but we don't send any privacy information. Oh, okay, click and you install it. And for the rest, it just runs in the background and does its stuff. So in short, this is a service, so it means it runs in the background. It zips and transmits the data from the memory card. It monitors for incoming calls, outgoing calls, and sends text messages with the information to the phone number that belongs to the dead guy. So the phone was bugged. Okay, so we actually got the case for the SwiftLogic guy. We pretty much know how the information from his phone got sent to, well, apparently the dead guy's phone. But now you want to know from the dead guy, okay, what is his connection? Why is he interested in this? And remember that when we got the images from the dead guy's phone, they were corrupt. The out-of-band bytes were missing. So we need some method to still investigate his phone images, but we can't just reconstruct the file system. Now, before I get into how we did it, I want to tell something about the JOFS file system. How many of you are familiar with the JOFS2 file system? Okay. So this is a good slide, I guess. Well, it stands for yet another Flash file system, version 2. It's a log-structured file system, so that means instead of what you normally see with most file systems, well, on hard disk storage devices, you have sectors, and a file has certain sectors, and when something changes in a file, the change is actually written in the sector where it is changed, right? If you have NAND flash, most modern NAND flash devices don't allow to just update bytes in a NAND flash page. So what you actually need to do is rewrite the page to a new empty page with the update in it. Now, Flash, JOFS was made for NAND flash, so what they did is instead that changes are written in the page itself, it actually rewrites the page and appends it after the last written page. And I will show that in an illustration, just this next slide. So data is never written in the same place, and it's strictly sequential. So within a block, each new page write is written after the last written page. Well, this is actually a very simple concept. That's why it was used in Android phones, because it's relatively lightweight and effective. However, it's single-threaded only. And that was good until we had the dual cores and the quad cores, and then it becomes a problem. So now the newer devices have X4, I think, or X3 on a flash transition layer. But until Android 2.2, it was all JOFS2. So JOFS concepts which are important, we have objects. JOFS calls it an object which can actually represent a file or a directory or a hard link. soft link or a device file, for example. JAWS speaks of chunks, and a chunk is, well, you could say it's a page in the NAND flash devices. It is possible if you have multiple parallel NAND flash devices that a chunk is actually multiple pages, but for simplicity we'll just refer to it as a page. And it has blocks, like every NAND flash. Data is written in pages and actually erased in blocks, and a block is, well, can be an arbitrary number from 32 to, say, 128 pages. You have the object headers, which is actually a chunk containing the metadata of a file, so a timestamp, for example, or the file name, permissions. That sort of stuff is stored in the object header, and you have a data chunk, and the data chunks contain the actual data of the objects, say the data of a file, for example. Okay, so how does it work? Here we look at a simplified version of a NAND block. We see the pages. In this case, on these devices we investigated, the pages were 2 kilobytes large. They can be 4 or 1 or 512 bytes. And after each 2 kilobyte chunk, there is the out-of-band bytes. And I think for this device it was 64 bytes. So each page has a small portion of out-of-band bytes. JAWS relies on the out-of-band bytes. It needs that section to store tags. And the JAWS uses these tags to link the pages, the chunks, to each other and to the object. So what you see when a file is written, this is an example of a file which is 2 pages long. You see 2 data chunks written and a object header. Now these 3 are linked by the object ID, which is written as a tag in the out-of-band bytes. So this is object ID 1, so it's the first file that is written. And the chunk ID is the identifier which tells you which in a sequence chunk of data it is in this object. So the object header has always chunk ID 0. The first data chunk has chunk ID 1, second has chunk ID 2. Now a second file is written, and you see that it's just appended in the next pages. Again, 1 data chunk is written, it's a very small file, and an object header is written. This has object ID 2, chunk ID 1, and 0. So now say we change something in the first page of the first file with object ID 1. Instead that the data is written in the first page is rewritten right after the last written page, and the header is rewritten because the timestamp, for example, is changed, or the size of the file is changed. This is all data that is stored in the object header, so that needs to be changed, so the page needs to be rewritten. And this is actually a very simple mechanism, and it's also very nice when you investigate flash devices, because this means that a lot of history is stored on the device. You can imagine that if you write to hard disks that the actual sector is changed, that the old versions are harder to recover. In NAND flash, all the old versions exist, will still be there until, of course, the whole block is erased to be reused. And that happens usually after a garbage collection. Fortunately, mobile devices are not very eager to start garbage collecting because it costs a lot of resources and makes your phone slow. So it will try to keep those blocks dirty and used as long as possible until it's really necessary to start cleaning it up, which is a good thing for a forensic investigator. Okay, so yeah, that guy's phone is posing a challenge for us. We know how the JAWS file systems work, and we can't reconstruct this because we don't have the out-of-band bytes. All the interesting stuff is on the internal user data partition. Now you could say, okay, why don't you just use the traditional carving tools like we did in the beginning? Well, there's a slight problem with that because all the interesting information is in SQLite databases. Android stores contact information, SMS messages, email messages. Most interesting information is stored in SQLite databases, which is just, well, sort of automatically done by the OS API when you store data. And SQLite databases don't really have a nice file format for carving. They have a specific header. They have a magic string in the header. You can look for that in raw data and say, okay, this is probably a starter of a SQLite database. But the SQLite databases don't have a nice footer. So you can't say with certainty, okay, this is the end of a file. And even if they had it, because of the high fragmentation of the YOFS file system, so each change, even if it's 1 byte in an SQLite database, is rewritten somewhere in a completely different part of the file system, of the YOFS image. So it's very hard for linear carving tools to just start, okay, this is the start of the file, and then you look for a footer which can be on the other end of the YOFS image. So you get a lot of garbage with that and very little useful information. So we need a smarter way to actually carve the data. To carve for SQLite format, SQLite database, it's important to understand the SQLite page. Now, very simply put, SQLite databases are stored in a balanced tree form. So there's always a root page, and it has references to interior pages, and those pages have reference to other pages, and then at the bottom, we have the leaf pages. Now, the root page contains a magic value, so you can recognize a root page. An SQLite page can have a size of 512 bytes to 64 kilobytes. They will probably design SQLite pages to fit into a YOFS page because that's more efficient. All the actual data, all the records of a SQLite database are stored in the leaf pages. So that's what we are looking for. We don't really care about the interior pages or the root page. We want the real data. Now, very simply, the format of a SQLite leaf page is you have a page header, and I will show that in detail later. You have a cell pointer array, which actually is just an array of offsets in that page where the cells, where the records are stored. So we can use that as a guideline to look in that page for where the records are. And you have the cell content area, which stores the actual table records. So this is the pages. These are the pages we want to look for in our raw YOFS2 image. So the idea is we want to carve the SQLite data from a raw YOFS2 image on a record level, so we don't carve for the whole SQLite database file because that appears to be too difficult. So we start carving for records of an SQLite database. And the nice thing in the process is we can get a lot of deleted previous history information from the YOFS2 file system if we do it correctly. So step one is to identify the SQLite leaf pages, right? So we want to recognize in our YOFS2 raw image when a SQLite leaf page starts. Well, fortunately, the SQLite leaf page has a sort of recognizable header. We know that the pages are a multiple of, you know the page size because it's set in the database header. So if you look at the database files in a reference phone model, you can see what page size is used. So knowing that page size, you can start looking at the boundaries of these page sizes. In this case, it was, I guess, 2 kilobytes. You can start looking at the boundaries of these pages for the signature of a leaf page. So this is the format of a leaf page. You can see that in the beginning, a leaf page is always identified by 1 byte, which must have the value 13. Now, if you start looking to your image purely on the borders and on this, only this byte, then you get a lot of garbage because there's going to be a lot of false positives. So we need more bytes to have a better algorithm for detecting the leaf pages. Well, there's also a byte which tells you the byte offset into the page, and we know that the value of that byte must be smaller than the page size. So we can check for that. If the second byte, the second 2 bytes make a value which is smaller than the page size, then it's more likely that this is a leaf page. And so we can do it with the rest of the bytes also. So you create a kind of heuristic to recognize a leaf page. If all those bytes match your criteria, then it's very likely that it's a leaf page. Okay, so we can now identify the leaf page, the SQLite leaf pages. That's great. We can carve out the leaf page, and then we want to look for the records inside this leaf page, because that's what we're interested in. Now, there was a cell pointer array, which is actually just offsets into that page where the records are stored. For this example, we see that there's 2 records stored here. Well, actually 2 cells. Cell 1 is located at the offset 279 and the other at F1. Now, when we look into this page, you can now nicely carve out the cells from this page. This one has only 2. You see the colored in yellow and green. So for this page, we now carved out 2 cells which contain the records of the SQLite database. Now we have another challenge because we have an anonymous record. We have multiple anonymous records. We know that there's SQLite data in there, but we actually don't know to which database or table in the database it belongs, because the SQLite schematic of the table or the database is not stored with the records, but it's stored somewhere at the beginning of the file. Now, if you look at the format, you see that there's a payload size, a row ID. This is usual in database tables. Then you have a section which defines the column types. So, for example, it says the first column is of type integer, the second is a string, the third is a string, the fourth is a blob, and etc. And then you have the actual column values. Now, the last 2 parts, the column types and the column values, together is called the record. That's the information that's interesting for us. So then you want to, now that you know the column ID, the types, you can actually match them against templates you create. So when you take a known database file from an Android phone, for example, take the contacts database, you take a reference model and you look at the format of the table, you know which columns there are in the table and of which type they are. So that allows you to create a template. So this is one example from the calls file. We know the columns, how many columns, and we know the types of the columns. Now we can match all the records we found, the anonymous records against this template, and actually categorize it into which table it belongs. And we did that, and that worked pretty well. Here's an example of what we recovered. You see here a nice table of contact information. So the table above is the call log, so outgoing and the incoming calls, and the second table is the contact table. This table is more interesting because this is actually the text message database. And what you see here is, when you look at the row IDs, is that you see always multiple versions of the same row. Well, that's due to the JOVS file system. So when you look at the example of row 155, you see that he is sending it, he's creating a message, and the first status is a draft. Now when you send the message, the status is changed to pending and then send. Each time the status is changed in the SQLite record, the whole page, the whole JOVS page needs to be rewritten. So that's why we can see the history of what happened to that record. So you can see here when it was drafting his message, and you can see exactly when he actually sent the message. That's really nice. And what's more is when you look at the top messages, you see the text message package uploaded. Now this was a text message that we saw is sent when the application on the SwiftLogic2's phone, the malware, actually uploaded the zip file. It sent this text message with this format. So this actually connects the dots of this phone. And when you look through the SMS messages, you see that he's communicating with a certain person, that's Mr. E. about that he has a sample and he wants more money. This is the browser history. This is also a nice example. The older versions of Android just stored your credentials in clear text in the SQLite database. That's bad for the user, I think, but good for the forensic investigator because he can use that information. And at the bottom, you see the visits to the actual web server where the PDF files were hosted. And the nice thing is that also here you can see, due to the DFRWS file system, the version history. So you see the first records actually show he first visits the page, and then that was one visit, and then the next one you see the second visit. Normally, when you look at the browser history, you would only see the last record that he had 2 visits. But now you can also see, due to the version history, that his first visit was at 5:59 and his second visit was actually at 6:28. So this gave us a lot of information about what happened on the phone. And you can see here that he searched on Twitter for on the SwiftLogic guy. So this method really helped us to actually, from a big blob of JOVS2 data, which cannot be reconstructed into a file system, to still get all the interesting information out of there on a really low level. Now this method is also applicable to your traditional hard drives. So when you want, for example, to search in deleted data, instead of looking for whole SQLite database files, you can carve on records, which will get you even more data back than looking for the whole SQLite database file. Well, that was actually what we needed to reconstruct the story. Other findings we had, which I didn't discuss today because of the time. There was a Facebook post from the SwiftLogic dude in which he says, hey, tonight I'm going to pick up my new phone. That Facebook post was read by the dead guy, and he called to the phone store where the SwiftLogic guy was going to pick up the phone. So it's likely that he had a little chat with the phone store manager and asked him to somehow install the package on the SwiftLogic dude's phone. There's a lot of communication between the dead guy and a certain contact named Mr. E, in which he discusses that he has some results and that he wants more money. And they make an appointment, and, well, the result is that he's dead. So, well, in a nutshell, he bugged the phone, the dead guy bugged the phone of the SwiftLogic dude, and he got the sensitive data out of there, the schematics of SwiftLogic. The dead guy downloaded the schematics, had contact with Mr. E, said, hey, I have the stuff, I want more money, and Mr. E probably killed him. So that was basically the Digital Forensic Research Workshop Challenge. If you want to read more, you can, it's all published. You can look it up. It was a really cool challenge. There were a lot of new aspects in there. By now, the new phones don't have JOVS2 anymore, but there are still a lot of phones out there with Android 2.2 or lower, so it's still actual now. Thank you for your attention. I hope you enjoyed it.
Thank you very much, Ivo. We've got about 10 minutes left for questions. I'm not sure if anyone has any questions they'd like to ask. Oh, right.
Thanks. You said the new phones use X4 and stuff. That goes to a flash translation layer. Does that translation layer do some sort of history sort of stuff like the FS2 for obviously flash performance? And can you get to that data and get history on that also?
So I understood very little of what you just said.
So the new phones use X4,
yeah,
and they go through a flash sort of translation layer, and I presume that will have some kind of not rewriting to protect the flash again. So can you get the history still there?
Actually that goes for all the NAND flash file system, is that as long as the blocks are not flashed and data is changed, it's written to new pages and the old version remains. So that the same goes for the new file system. but it depends on how it's implemented. If, for example, I know of operating systems that when you actually rewrite a file or you delete a file, that the whole block is immediately wiped. So that would kind of destroy your previous versions. But I don't know for sure how it is with the newer Android phones. I haven't really looked into that yet.
Okay. Anyone else? Yeah.
Great talk, thank you. Just a quick question. How does the forensic industry, the forensic laws, and all the legal framework go along with, let's say, rooting a device? Because does rooting a device is a sound forensic measure? Because, I mean, you root, you actually can taint the device and the evidence, right?
Yeah, that's a good question, because they don't really like that. Well, in the Netherlands it's not so much of a problem, but I believe in the United States that's much more of a problem if you change data on the device. What we see with the newer rooting techniques, that it's possible to do well, actually a temporary root, which only operates in the memory of the device. So that's the nice thing. You just temporarily root the device, then you acquire, and you actually run your tools from the memory, and you acquire the data from the partitions without changing anything on the partitions. You don't even change the system partition. So the newer techniques are helping us with that. Yeah.
Okay, any other questions for Ivo? No. All right, well, Ivo, thank you very much again, and we'll be right back and set up the next speaker for you. So thank you.
Thanks.